Hello guys, this is CodeNCode and this is the fourth lecture of this graph theory series part 2, and in this lecture we are going to study about LCA, that is lowest common ancestor. So this is the part 2 of this LCA lecture. So I advise you to study part 1 first and then come here, because this is in direct continuation to that lecture. So just watch the lecture 1, part 1 of the LCA lecture, since this is part 2. So let's continue. So if you remember from the previous lecture, the LCA function takes two parameters a and b, which are nodes of the tree, and then we calculate the difference between their levels. If level of b is smaller than level of a, which means a is deeper than b, but we want b to be deeper, so we would simply swap a and b, and then we would calculate the difference between their levels. And while d is greater than 0, that is while there is difference between their levels, we would update b, or we would lift up b to b is equals to parent of b, and then we would decrement the difference between their levels till d is greater than 0. And if a is equals to b, we know a or b are the ancestors or LCA itself, so we would directly return a. Otherwise we would now start lifting at this point a and b both are on the same level, like on this point say. So we would start lifting a and b one by one together till parent of a is not equal to parent of b, and after that point parent of a or parent of b would be your LCA. I've explained all of this. This is basically your naive approach. I've explained everything of this code in the previous lecture, so if you have no idea what this is, just go and check out lecture 1. So in the previous lecture I've given you also a homework to think about the jump. The problem with this approach is that we are making a jump of length 1, which leads us to a time complexity of big O of n, because of the linear jump, because of jump of length 1. So I've asked you to think about alternative length jumps. So the best way to jump is in power of 2. So instead of making a jump of length 1, we would make a jump of highest length L, such that L follows these two properties. First, L is a power of 2 and L is less than equals to D. So suppose D was 13, so the difference between node A the level difference between the levels of node A and node B was 13. So the highest power of 2 such that L is less than equals to 13 is 8. So we can make a jump of length 8 directly. So now the distance would be 5. Now the highest power of 2 such that it is less than equals to 5 is 4. So we would make a jump of length 4. And now D is 1, so the highest power of 2 such that it is less than equals to D is 1. So we would make a length 1 jump, and finally we would be there. So D would be 0. Now see, even the distance was 13, we are able to cover it using 3 jumps. See, so this thing, if you observe closely, is actually binary representation of 13. So binary representation of 13 is actually 2 raised to power 3 plus 2 raised to power 2 plus 2 raised to power 0. So what it tells you is that you can actually calculate the distance, or you can actually cover the distance if you are making a jump of this thing, the highest length L, such that L is less than equals to D. If you are making a jump of L each time, then the complexity would be log n, because you would be able to cover the distance in log n time. Reason, each time when you find L, which is highest power of 2, such then L is less than equals to D, L is actually at least half of D. So and you can prove this fact that L is at least half of D using proof by contradiction. It is easy to prove. So you can, I'm leaving it as an exercise for yourself. It is literally too easy to prove, so leaving this as an exercise. So L is at least half of this. So what is happening here? D is being each time decreased by half. So D would be, in the next step, would be at least D by 2. In the next step it would become D by 4, and in the third step it would be D by 8, and so on. So you see, D is being decreased, D is basically is being cut down in half in every operation. So there won't be more than log n operation, or basically there won't be more than log n jumps. So whatever D is there, D can be in the worst case n minus 1. So you won't be making more than log n jumps. So we are able to cover the distance between A and B in log n time, which was previously big O of n time. So this is a great improvisation from big O of n to log n. But see how we were able to make a jump of length 1. For that we were having an array parent. So when B was this and I have to go all the way till this point, so what we were doing is that updating B is equals to parent of B, and parent of B is this, so B would be updated to this. Now this node also is having stored its parent somewhere in the parent array. So again we would update B is equals to parent of B. So we are here, B is equals to parent of B, and we are here. Now to make a jump of length 1 we were using parent array. Now since we want to make jump of length L, which is actually power of 2, we have to save for each node every power of 2 possible. So for this node we need to save 2 to the power 0, which is this direct parent, 2 to the power 1th parent, which is this, then 2 to the power 2nd parent, which would be this because it is at length 4, and finally 2 to the power 3rd parent, which doesn't exist, so we don't have to go till that. For each node we have to keep all parent of this, or basically all power of 2. For that, how many parents do we have to store for each node? Because this, as you can see, for this node we have to keep a list of length 3 because 0th parent, 2 to the power 0th parent, 2 to the power first parent, and 2 to the power 2nd parent. So we have to keep a list of length 3 for this node. Same goes for this node, and for this node we have to keep a list of length 2, which is 2 to the power 0th parent and 2 to the power 1th parent. So the problem is, what would be the space complexity? So for each node we have to keep a list of at max log n number of nodes. The reason, suppose I is the highest node, such that for a node, say this or any another node, I is the highest power of 2 which we need to save, because we are saving parents which are power of 2. So I is the highest power of 2 such that I is less than equals to n. So if you take log base 2 on both of the sides, I would be less than equals to log n. So what it tells you is that for each node you don't have to make a list of more than log n nodes. So since there are n nodes in total in the tree, so the overall space complexity would be n log n, because for each node you have to keep a list of log n parents. So there won't be more than log n parents of each node, and since there are n nodes, so the overall space complexity would be n log n. So we would keep, since n is the number of nodes and max n, the maximum power of 2, would be log base 2n, since we don't have to make a list of more than log n nodes. Now we would have, a 2D array called LCA, to store all the list of the nodes, all the list of the parents of each node. So and LCA would be 2D array, where the first dimension is for nodes. So since there are n nodes, so we would declare the first dimension would be n+1, and the second would be max n, because this is the maximum number of parent each node can have. So LCF ij would be representing 2 raised power jth parent of node I, since this represent I and this represent the power of 2, so basically 2 raised power jth parent of I. So now for this tree, suppose since there are 8 nodes, so we would be taking LCA of size 8 3, because log base 2 of 8 is 3, so we would be taking 0 1 2 3. Yeah, so the column represent 2 raised power 0th parents, so this is actually row 1 2 3 4 5 6, this is row, and this is column from 0 to 3. So this cell represent 2 raised power 0th parent of node 1. This cell represent 2 raised power second node of 2 raised power second parent of node 1, and so on. So this is your LCA array. Now the question is, initially you would fill all the values with -1, indicating that none of the parents exist. Now to fill this array, first of all we need to find 2 raised power 0th parent. 2 raised power 0th parent means the direct parent of each node, right? So to fill this, all you can do is simply make a DFS run, and then using a simple DFS run, 2 raised power 0th parent of each node can be calculated. So the parameter contains two things. First is node, and second is its parent. So if you are on node 6, so node would contain 6 and parent would be equal to 2, because parent of 6 is 2. So in the LCA array of node, the 2 raised power 0th parent is actually its parent. So this is how we would initialize the LCA 0th column of LCA array. Now in the adjacency list of this node, we would make DFS call, and remember here we are not using the visited array to keep track of the nodes which have already been visited. So we need this parent to keep track of the nodes that we don't have to make call again. So since on node 6 you would come from node 2, because 2 is parent of 6, so DFS call to 6 was made from 2, so you don't have to make a DFS call back to node 2. To make sure that what we are doing here, if in the adjacency list of node 6, if the child is not equal to parent, that is if child is not equal to 2, then we would be making DFS call to that. I hope you already know how this works, this DFS run without using visited array. So this is simply DFS without using visited array. So if in the adjacency list of node, if child is not equal to parent, we would make DFS call to that node as well. And after the execution of the DFS is completed, we would be having LCA of 0th column of LCA array ready. From main function we would be making a DFS call to node 1, and since node 1 is having no parent at all, so as parent we would pass -1. So from main function we would make a DFS call to DFS 1 -1. After that the 0th column is prepared. Now since we had passed for node 1 the parent as -1, so of course LCA 10 would be -1. LCA 20 would be 1, indicating the 2 raised power 0th parent of node 2 is 1, which is direct parent, and for 5 direct parent it is 2, as you can see. So the 0th zeroth column is ready, which means 2 raised to power we know for each node 2 raised to power zeroth parent of it. Now we need to prepare or basically fill the values of 2 raised to power 1th column, or we have to find 2 raised to power 1th parent of each node. Now we can't make a DFS call again. If we do that, the complexity would be too high. For a node list of like n is equals to 10 to the power 6, you are sure to get TLE if you run log n time DFS. So it's not a good idea to run DFS each time. Instead, we can use dynamic programming to fill the rest of the values. We need a simple observation and then dynamic programming. The important observation here is that, see, now we are going to calculate 2 raised to power 1th parent, right? So 2 raised to power I can be written as 2 times 2 raised to power I minus 1, right? 2 raised to power 5 is equals to 2 times 2 raised to power 4, which is actually the same thing. So what you can do, you can prepare the 2 raised to power 1th list from 2 raised to power 0th list. And since 2 raised to power 0th list is already prepared for us, we can prepare 2 raised to power 1th list. I'll tell you how. So suppose for node 5 we have to find its 2 raised to power 1th parent. 2 raised to power 1th parent, which means the parent which is at distance 2, at distance 2 raised to power 1, which is 2. So for node 5, 2 raised to power 1th parent is 1, right? So how we can calculate it? For as we explained earlier, 2 raised to power I can be written as 2 times 2 raised to power I minus 1. So to calculate 2 raised to power first parent, I'm going to use 2 raised to power 0th parent. So for 5, I'm going to ask it, who is your 2 raised to power 0th parent? So 2 raised to power 0th parent of 5 is 2. So 2 is my intermediate node. Now I would ask 2, who is your 2 raised to power 0th parent? So 2 raised to power 0th parent of 2 is 1. So this is my 2 raised to power 1th parent. So how we calculated it? We first, for node 5, we found its 2 raised to power 0th parent. So 2 raised to power 0th parent was this, which is intermediary node for now, and 2 raised to power 0th parent of this node is 1. So 2 raised to power 1th a node of 5, or 2 raised to power 1th parent of 5 is actually 1. Why is that so? Because the distance between this and intermediary node is 2 raised to power I minus 1, and the distance between intermediary node and its 2 raised to power I minus 1th parent is again 2 raised to power I minus 1. So 2 times, so the distance from here to here is actually 2 raised to power 2 times I minus 1, sorry, 2 times 2 raised to power I minus 1, which is 2 raised to power I. So to calculate 2 raised to power ith parent, we use the values of 2 raised to power I minus 1th parent. So taking an example of 7. So since we have to calculate 2 raised to power 1th parent, so first we would find the intermediary node, which is 2 raised to power 0th parent of 7. So 2 raised to power 0th parent of 7 is 6. We can calculate it from LCA array directly. It is 6. So now 6 is our intermediary node. Now we would ask 6, who is your 2 raised to power 0th parent? So 2 raised to power 0th parent of 6 is 2. So 2 is actually 2 raised to power 1th parent of 7. So this is how you calculate it. First you find the intermediary node, and it is easy. Suppose you were to calculate 2 raised to power 3rd parent. So what you would do, you would find for node 5, say. So first for node 5, you would find its 2 raised to power 2nd parent. That would be your intermediate node, and then using that intermediate node, you would calculate its 2 raised to power 2nd parent, and that would be your 2 raised to power 3rd parent. So if I take another example, and suppose we have to calculate 2 raised to power 2nd parent, which is 4th parent. So 4th parent of 8 is 1, 2, 3, 4, 1. So how you'd calculate it? Since you have to calculate 2 raised to power 2nd parent, first you would find intermediate node for 8. That would be 2 raised to power 1th parent. So 2 raised to power 1th parent of 8 is 5, which would be already calculated, because only after we have calculated for column 1, then only we would move to calculate column 2. So if we are calculating for 2 raised to power 2, 2 raised to power 1th column is already ready. So 2 raised to power 1th parent of 8 is 5. Now this is intermediary node. now we would ask this, who is your 2s power 1th parent? 2s power 1th parent is this. So now 1 is actually 2s power 2nd parent of 8. So you see, we can, in constant time, we can actually calculate the 2s power ith parent, or basically we can fill the whole matrix in n log n time. So after finding all 2s power 1th parent, this would look like this. So 2s power 1th parent of a node exists if 2s power 1th parent of node exists if and only if 2s power 0th parent exists, because we are using 2s power 0th parent to calculate 2s power 1th parent. So for this node, 2s power 0th parent must exist. So if you see, suppose I had to find the 2s power 1th parent of 1, but since 2s power 0th parent of 1 doesn't exist, which is -1, so it indicates 2s power 0th parent of 1 doesn't exist. So if 2s power I minus 1th parent doesn't exist, then 2s power ith parent doesn't exist as well. So if 2s power I minus 1th parent is -1, we would directly continue, which means we would ignore this. So if I show you the code, this is how preprocessing, or basically sparse table, is constructed. First, we would make a DFS call to node 1 because we are assuming node 1 is the root. So if you are taking any another node as root, so you would pass that node here. So I'm assuming node 1 is root, so I'm making a DFS call to root and passing -1 as its parent, since a root doesn't have any parent, that is why passing -1. After DFS, 2s power 0th parent is already calculated, so LCA of node comma 0 is already calculated. Now we have to calculate from 1 to max n, so that is why the first loop is from 1 to max n. Now after that, we are calculating for each node, that is from 1 to n, the jth parent. To calculate 2s power jth parent, as explained earlier, 2s power j minus 1th parent must exist. So if for node I its j minus 1th parent exists, then its value won't be -1. So if LCA of I j minus 1 is not equal to -1, then we would proceed. So we would find the intermediary node, which is LCA of I of j minus 1, basically your j minus 1th 2 power j minus 1th parent, that is your intermediary node. Using this intermediary node, we would find its j minus 1th parent, so that would be R, or node I is jth parent. So this is how preprocessing is done, or basically your sparse table is constructed. I haven't shown the process where you initialize the LCA array, each element of LCA array as -1. That is also important. Now after our LCA array or sparse table is constructed, how you are going to calculate how you are gonna apply the lifting. So as you can see, the difference between their level is of 5. So the highest power of 2 such that it is less than equals to 5 is 4. How do you calculate it? So it is very easy, just take log base 2 of 5. Log base 2 of 5 would be 2 point something something. If you save it in integer, it would be converted into 2. So it would be log base d currently would be 2, indicating you have to calculate 2s power 2nd parent. So in the LCA of b2, LCA of b2 would actually contain the 2s power 2nd parent of it, so we would update b is equals to LCA of b2, so it would directly make a jump of length 4, because 2s power 2nd parent is this for b. So now d would become 1. Now log base 2 of d, which is 1 actually, it would be 0. So what you have to do, you have to update b to be b is equals to LCA of b0, that is you have to take jump we have to update it to be its 0th parent. So if you update it to be its 0th 2s power 0th parent, it would become this, and now the distance would become 0. So this is how we make jumps. If I show you the code, it is easy, everything is almost the same. That is why I first explained the naive algorithm, because the difference between the codes of naive and the binary lifting is not much different. So first we check if level of B is smaller than level of A, we would swap A and B so that level of B is greater. So now we would calculate distance, level of B minus level of A. This is same as naive approach. Now here, while D is greater than 0, again same thing, but here now instead of making a jump of length 1, what we are doing here is that we are calculating I is log base 2 of D, and then we would update B to be LCA of BI, which is making a jump of length 2 raised to power I. Now since we have made a jump of length 2 raised to power I, we have to reduce 2 raised to power I from D. So D minus equals 1 left shifted I times, which is 2 raised to power I. So this loop would run at max log n time. Now if A is equals to B, return A. Again the same thing as naive approach. Now here this while loop was while parent of A is not equal to parent of B, A is equals to parent of A, B is equals to parent of B. This loop, again, the problem with this loop is that the speciality of this while loop is that it would run at max log n time, but the problem with this loop is that it would run again in the worst case in big of n time. So the overall complexity is still big of n, because this is again making a jump of length 1. The problem here, we can't make a jump of length greater than 1 is because we don't actually know at what distance. Now since we are at this point, which means A and B are on the same level, right? Now we don't know that at what distance does LCA exist. The LCA is at 1 distance or 2 distance, we don't know. Here while we were making a jump of in terms of power of 2, here it was able we were able to make those 2 raised to power ith jumps because we actually know the distance between the levels of A and B. So we were having a distance D, or basically the distance that we have to cover. Each time we can calculate its log, and then we know, okay, we have to make a jump of 2 raised to power I. But here we actually do not know at what distance does the LCA exist. So because of that, we have to make jump of length 1. To go around this problem, or to tackle this problem, what we can do, since we do not know what is the distance that we have to cover, so, and to counter that problem, what we can do is actually we can start making a jump of highest power. So the highest power of 2 is max n. As you already know, max n is actually log base 2n, which we have already defined. So we would start from max n. So suppose for this max n is actually 4, so we would see, okay, whether we can make a jump of length 2 raised to power 4 or not. So 2 raised to power 4 is actually 16. So does a 16th parent of B exist? So if you see 1 2 3 4 5 6, at max it has 6 parents, right? So 2 raised to power 4, which is 16, so 16 parent of neither A nor B exist. So how we can check that? You can check that using this. If 2 raised to power ith parent doesn't exist, then it would be minus 1. So first condition we would check whether LCA of A of I exists or not. For that we would check LCA of A of I is not equal to minus 1, which would ensure that, okay, the 2 raised to power ith parent at least exists. So now suppose max n was 4, so 16th parent doesn't exist, so that would be having minus 1. So we won't update A or B. Now I would decrease, I would become 3. So 2 raised to power 3, which is 8. So 8th parent exists or not? We see 8th parent doesn't exist because for A and B at max 6th parent exists. So again, since 2 raised to power 3rd parent doesn't exist, it would be minus 1. So we won't update again. Now I would decrease and I would become 2. 2 raised to power 2, which is actually 4. So 4th parent, yes, 4th parent of A and B exists. So 4th parent of A and B is this 1 2 3 4, this node. For A and B both, 2 raised to power 2, that is the 4th parent, is this node. So at least 4th parent exists. Now this condition would be true, but should we make a jump of length 4? The answer is no. You can see, because if we made a jump of this length, we would actually leave behind the LCA. LCA is this for A and B. So if we made a jump of length 4, we would actually leave behind the LCA. So how we can tackle that problem? You see, if we made a jump of length 4 for A and B, they both would land on the same node. So basically their 2 raised to power ith parent is actually same. So if you make a jump such that their parent is actually same, it would come with a cost that we may leave behind LCA. So we won't do that. So if the ith parent of A and B is same, then we would not make that jump as well, because that would come with a problem that it is possible that we are actually leaving behind the LCA, which we don't want. So if the ith parent of A and B are same, or basically 2 raised to power ith parent of A and B are same, we won't make that jump. So 2 raised to power second parent of A and B exist, so this condition is true. But 2 raised to power second parent of A and B are same, so this condition is false, so we won't update A and B again. Now I would decrease again, I would become 1. 2 raised to power 1, which is the second parent of A and B exists. Yes, second parent of A and B exists, so this condition is true. And the second condition is that 2 raised to power 1th parent should not be same. So we see 2 raised to power 1th parent of B is this, 2 raised to power 1th parent of A is this. So these two are different. So now we can update. A is equals to LC of A of I, that is 2 raised to power 1th parent of A, and B is equals to LC of B of I. Now A and B would become these two. Now since I was 1, now I would become 0. So 2 raised to power 0th parent of A exists. When 2 raised to power 0th parent of A exists, it means 2 raised to power 0th parent of B exists, because both of them are on the same level. So since 2 raised to power 0th parent of A exists, this condition is true. But 2 raised to power 0th parent of A and B both are same, so we won't make that jump. After that, I would again minus, and I would become -1, and hence we would come out of this loop. So this loop would run at max log n time, because max n is actually log n. So this loop runs in log n time, this loop runs in log n time, so the overall complexity is actually log n. After that, what we would do, after performing this loop, A and B would be just one jump behind their LCA. So you would simply return, I've by mistake written parent of A. Actually we have to return LCA of A of 0 or LCA of B of 0, which is their parent. So that node would be their LCA. So this was how you calculate LCA using a binary lifting, which runs in log n time. And for pre-processing, the complexity is n log n. Space complexity n log n, pre-processing time is n log n, because we have to construct parse table before we can actually calculate LCA. And now in each query, LCA can be calculated in log n time. So in the next video, I'll be explaining a problem which is actually calculate distance between two nodes, and that utilizes LCA. And each time you can calculate distance between two nodes in the given tree if you know their LCA in constant time. But since you take log n time to calculate LCA, so each query can be answered in log n time. So we will be solving the problem in the next lecture. So there I will also be showing you the explanation of or implementation of LCA. So till the next video drops, keep coding. Thank you.